morning. Sorry. Yeah, maybe. I need this microphone for you to hear me. Thank you very much for this opportunity to talk about coupling the human system with the Earth system, and a little bit about data assimilation in that way. So this is work that was done mostly by Safa Montesarrey and Jorge Rivas and myself, but as you will see, we have a paper also that had many famous authors, including Takemasa Miyoshi, so we are very honored for that. So the question, well, one question is population and climate change, and the main question that we are trying to address is, are we sustainable? And unfortunately, the answer is no. The way we are going, we are not sustainable. So we wrote 2 papers, and we have two more in publication. So one is the human and nature dynamical model, HANDI model. And actually we were very lucky because before it was published, it was blogged by a blogger in The Guardian, and the blog just went super viral, had 40 million hits, and maybe 10% were very negative about the paper. And we wrote another paper modeling sustainability, population, inequality, consumption, and bidirectional coupling of the Earth and human systems. And this has Takemasa, sorry, I'm nervous, and this magnifies my nerves. And Takemasa Miyoshi is one of the authors, and many other famous people like Mark Kane, Rita Colwell, and Tony Busalaki, many other very good scientists. And it's open access, and it is in the top 1% of the papers of the same age, so it's been quite popular also. But it is a very careful, I think, and a study of all, or discussion of all the phases of population, inequality, consumption, bidirectional coupling. And we conclude, just in case I don't talk anymore about data assimilation, we concluded that certain economic methodologies like input-output tables, and especially data assimilation, are very important for actually developing a coupled human natural system. We don't have currently a coupled natural and human systems that are realistic. So maybe the light is okay. Probably you cannot see much of this, but the climate change is obviously happening, and this was the hottest year on record, 2014, and then the following year was the next on record. And sorry, is that okay? Yeah. So 2016 was the next record, and apparently 2017 is about the same as 2016. So it's also sharing the record. So, but not just the greenhouse gases, but population has to be accounted, and we plotted with our colleagues, Jan Lian. This figure that has the evolution of the population, which is in red, and then the three leading greenhouse gases, carbon dioxide, methane, and nitrous oxide. And this is from 10,000 years ago to the present. So it starts when more or less the agricultural evolution started, and it is obvious that things are going out of control at this time. And now if we just start looking at the 1750, which is about the beginning of the Industrial Revolution, we see that there is a very strong growth, as shown here, but also in 1950 the slope suddenly changes. It becomes much stronger, and this huge acceleration at 1950 happened with the Green Revolution, and especially with the massive use of fossil fuels. And this is shown in this figure. It shows fossil fuels, cement and flaring, and this is forestry and other land use of anthropogenic CO2 emissions. And you can see clearly in 1950 is when the Haber-Bosch nitrogen fertilization started the Green Revolution, and it's very clear the impact. So it's not just burning fossil fuels, but nitrogen fertilization and use of tractors and irrigation also is a great produces a great consumption of fossil fuels. So since the 1800s, we are burning the fossil fuels that nature accumulated during hundreds of millions of years. This is such an incredibly different time scale. And by burning the accumulated carbon, we emit CO2 into the atmosphere, and CO2 acts like a blanket, greenhouse effect. So the atmosphere is warming up. But the total emission is the product of population and emission per person. So we have to look both at population and emission per capita. And there was it's interesting that the United Nations is increasing by billions, 1 billion every few years, the estimated projection of the maximum. It used to be thought that population is a solved problem. Naturally, the population will stop growing or decrease, but that's not happening. So there was a study in the London School of Economics that considered this population and emission per person, and concluded that per dollar spent, family planning reduces 4 times as much carbon over the next 40 years than adopting just adopting low carbon technologies. And why was the population able to grow so fast since the 1950s? One is sanitation and antibiotics, so people live longer. But very importantly, the Green Revolution, the use of fossil fuels in agriculture starting in the 1950s, so there are fertilizers, pesticides, irrigation, mechanization. And the result was that between 1950 and 1984, the production of grains increased by 250%, and the population doubled. And without fossil fuels, population would be much smaller. But now, the growth in grain production is flattening out, and industrial farming is destroying forests, soil, and aquifers, and urban and suburban sprawl is overrunning the best farmland. And this is just not sustainable. Herman Daly, a very famous economist who invented ecological economics, in which the Earth system is included, he said, we are drawing down the stock of natural capital as if it was infinite. And it's not infinite. And this is the way the neoclassical economic models work. You have firms that produce goods and services, and to households that produce labor and capital, and this can grow and grow and grow forever. This does not include the input, the resources that are needed from the nature, the dissipation of energy, destruction, and so on. So this theoretical idea, neoclassical economics ignores the effects on the Earth system and has no limits to growth. And so Herman Daly, who is a professor, or was a professor at UMD also, introduced ecological economics within the Earth system. So he said we have to consider the Earth system and the human economy that has population, technology, and all sorts of things. And it requires inputs like energy, oil, coal, etc., and matter, minerals, lumber, etc. So these inputs require sources of natural capital and also flow of energy. So this goes into the human economy, and the output is basically garbage. The emissions, waste products, and surface changes, urbanization, deforestation, desertification, etc. And that garbage goes into the sinks, which are the oceans, the atmosphere, and the land. So on top of that, we have important feedbacks. So, for example, the sinks affect, for example, the fish, and we are overfishing, and that reduces the resources, and same with land and the atmosphere. And also the outputs reduce the natural stocks. So we didn't need to worry about that before the Industrial Revolution. The human system compared to the Earth system was tiny, and so we didn't need to worry about inputs and outputs because it was small. But so this could have been called an empty world before the Industrial Revolution. But now, especially after 1950, we are in a new geological era, the Anthropocene, and basically we are completely overwhelming the natural system and deplete, and this threatens to deplete the sources and overwhelm the sinks. We are not like this. We are like this, so we have to include the interaction. And this is a figure that shocks me every time I see it. It shows the population in billions from year 0 to 2000 in red, and the consumption, the GDP per capita also estimated for that period, and especially after 1950, it grows very, very fast, and the total growth is the product of this. So we are growing about 2% per year in population and 2% per year of GDP per capita, so about almost 4% per year. So since 1950, we are doubling our consumption every 17 or 20 years. So we are already consuming about twice what the Earth produces and doubling consumption every 20 years, which is obviously not sustainable. This is an example of global inequality, and it shows that of the total population, the top 10%, which is the people that are making over $23 per day, which is not much for many of us. And that 10% essentially uses half of the energy, and the per capita footprint of the bottom 90% of the population is an order of magnitude smaller than for the richer.